Part 2, Chapter 2 of A Popular History of Astronomy during the 19th Century. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. A Popular History of Astronomy during the 19th Century by Agnes Mary Clerke. Chapter 2, Solar Observations and Theories, Part 2. By its rotation, the Sun itself offers opportunities for bringing the stereoscope to bear upon it. Two pictures taken at an interval of 26 minutes show just the amount of difference needed to give, by their combination, the maximum effect of solidity. De la Rue thus obtained in 1861 a stereoscopic view of a sunspot and surrounding faculae, representing the various parts in their true mutual relations. I have ascertained in this way, he wrote, that the faculae occupy the highest portions of the sun's photosphere, the spots appearing like holes in the penumbrae, which appeared lower than the regions surrounding them. In one case, parts of the faculae were discovered to be sailing over a spot apparently at some considerable height above it. Thus, Wilson's inference as to the depressed nature of spots received, after the lapse of not far from a century, proof of the most simple, direct, and convincing kind. A careful application of Wilson's own geometrical test gave results only a trifle less decisive. Of 694 spots observed, 78% showed, as they traversed the disk, the expected effects of perspective, and their absence in the remaining 22% might be explained by internal commotions producing irregularities of structure. The absolute depth of spot cavities, at least of their sloping sides, was determined by Father Secchi through measurement of the parallax of profundity, that is, of apparent displacements attendant on the sun's rotation due to depression below the sun's surface. He found that in every case it fell short of 4,000 miles and averaged not more than 1,321, corresponding on the terrestrial scale to an excavation in the earth's crust of 1 1/5 miles. Of late, however, the reality of even this moderate amount of depression has been denied. Mr. Hallett's persevering observations, extending over a third of a century, the results of which were presented to the Royal Astronomical Society in December 1894, availed to shatter the consensus of opinion which had so long been maintained on the subject of spot structure. It has become impossible any longer to hold that it is uniformly cavernous, and what seem like actually protruding umbrae are occasionally vouched for on unimpeachable authority. We can only infer that the forms of sunspots are really more various than had been supposed, that they are peculiarly subject to disturbance, and that the level of the nuclei may rise and fall during the phases of commotion like lavas within volcanic craters. The opinion of the Kew observers as to the nature of such disturbances was strongly swayed by another curious result of the statistical method of inquiry. They found that of 1,137 instances of spots accompanied by faculae, 584 had those faculae chiefly or entirely on the left. 508 showed a nearly equal distribution, while 45 only had fasculous appendages mainly on the right side. Now, the rotation of the sun as we see it is performed from left to right, so that the marked tendency of the faculae was a lagging one. This was easily accounted for by supposing the matter composing them to have been flung upwards from a considerable depth, whence it would reach the surface with the lesser absolute velocity belonging to a smaller circle of revolution, and would consequently fall behind the cavities or spots formed by its abstraction. An attempt, it is true, made by M. Wilsing at Potsdam in 1888 to determine the solar rotation from photographs of faculae had an outcome inconsistent with this view of their origin. They unexpectedly gave a uniform period. No trace of the retardation poleward from the equator shown by the spots could be detected in their movements. But the experiment was obviously inconclusive, and M. Stratonoff's repetition of it with ampler materials gave a full assurance that faculae rotate like spots in periods lengthening as latitude augments. The ideas of M. Faye were on two fundamental points contradicted by the Kew investigators. He held spots to be regions of uprush and of heightened temperature. They believed their obscurity to be due to a downrush of comparatively cool vapours. Now M. Chacornac, observing at Villeurbanne, March 6, 1865, saw floods of photospheric matter visibly precipitating themselves into the abyss opened by a great spot, and carrying with them small neighbouring maculae. Similar instances were repeatedly noted by Father Secchi, who considered the existence of a kind of suction in spots to be quite beyond question. The tendency in their vicinity, to put it otherwise, is centripetal, not centrifugal, and this alone seems to negative the supposition of a central uprush. A fresh witness was by this time at hand, the application of the spectroscope to the direct examination of the sun's surface dates from March 4, 1866, when Sir Norman Lockyer, to give him his present title, undertook an inquiry into the cause of the darkening in spots. It was made possible by the simple device of throwing upon the slit of the spectroscope an image of the sun, any part of which could be subjected to special scrutiny, instead of, as had hitherto been done, admitting rays from every portion of its surface indiscriminately. The answer to the inquiry was prompt and unmistakable, and was again in this case adverse to the French theorist's view. The obscurations in question were found to be produced by no deficiency of emissive power, but by an increase of absorptive action. The background of variegated light remains unchanged, but more of it is stopped by the interposition of a dense mass of relatively cool vapours. The spectrum of a sun-spot is crossed by the same set of multitudinous dark lines, with some minor differences visible in the ordinary solar spectrum. We must then conclude that the same vapours, speaking generally, which are dispersed over the unbroken solar surface, are accumulated in the umbral cavity, the compression incident to such accumulation being betrayed by the thickening of certain lines of absorption. But there is also a general absorption, extending almost continuously from one end of the spot spectrum to the other. Using, however, a spectroscope of exceptionally high dispersive power, Professor Young of Princeton, New Jersey, succeeded in 1883 in resolving the supposed continuous obscurity of spot spectra into a countless multitude of fine dark lines set very close together. Their structure was seen still more perfectly about 5 years later by M. Dunet, director of the Upsala Observatory, who traced, besides some shadowy vestiges of the crowded doublets and triplets forming the array, from the spots on to the general solar surface. They ceased to be separable in the blue part of the spectrum, and the ultraviolet radiations of spots show nothing distinctive. As to the movements of the constipated vapours forming spots, the spectroscope is also competent to supply information. The principle of the method by which it is procured will be explained farther on. Suffice it here to say that the transport at any considerable velocity to or from the eye of the gaseous material giving bright or dark lines can be measured by the displacement of such lines from their previously known normal positions. In this way movements have been detected in or above spots of enormous rapidity ranging up to 320 miles per second, but the result so far has been to negative the ascription to them of any systematic direction. Uprushes and downrushes are doubtless, as Father Corti remarks, correlated phenomena in the production of a sun-spot, but neither seem to predominate as part of its regular internal economy. The same kind of spectroscopic evidence tells heavily against a theory of sunspots started by Faye in 1872. He had been foremost in pointing out that the observations of Carrington and Spurrer absolutely forbade the supposition that any phenomenon at all resembling our trade winds exists in the sun. They showed, indeed, that beyond the parallels of 20 degrees there is a general tendency in spots to a slow poleward displacement, while within that zone they incline to approach the equator, but their proper movements gave no evidence of uniformly flowing currents in latitude. The systematic drift of the photosphere is strictly a drift in longitude. Its direction is everywhere parallel to the equator. This fact being once clearly recognized, the solar tornado hypothesis at once fell to pieces. But M. Faye perceived another source of vorticose motion in the unequal rotating velocities of contiguous portions of the photosphere. The pores with which the whole surface of the sun is studded he took to be the smaller eddies resulting from these inequalities, the spots to be such eddies developed into whirlpools. It only needs to thrust a stick into a stream to produce the kind of effect designated, and it happens that the differences of angular movement adverted to attain a maximum just about the latitudes where spots are most frequent and conspicuous. There are, however, grave difficulties in identifying the two kinds of phenomena. One, already mentioned, is the total absence of the regular swirling motion in a direction contrary to that of the hands of a watch north of the solar equator, in the opposite sense south of it, which should impress itself upon every lineament of a sun-spot if the cause assigned were a primary producing and not merely, as it possibly may be, a secondary determining one. The other, pointed out by Young, is that the cause is inadequate to the effect. The difference of movement, or relative drift, supposed to occasion such prodigious disturbances, amounts at the utmost for two portions of the photosphere 123 miles apart to about 5 yards a minute. Thus the friction of contiguous sections must be quite insignificant. A view better justified by observation was urged by Secchi in and after the year 1872, and was presented in an improved form by Professor Young in his excellent little book on the Sun, published in 1882. Spots are manifestly associated with violent eruptive action, giving rise to the faculae and prominences which usually garnish their borders. It is accordingly contended that upon the withdrawal of matter from below by the flinging up of a prominence must ensue a sinking in of the surface into which the partially cooled erupted vapours rush and settle, producing just the kind of darkening by increased absorption told of by the spectroscope. Round the edges of the cavity, the rupture of the photospheric shell will form lines of weakness, provocative of further eruptions, which will in their turn deepen and enlarge the cavity. The phenomenon thus tends to perpetuate itself until equilibrium is at last restored by internal processes. A sunspot might then be described as an inverted terrestrial volcano, in which the outbursts of heated matter take place on the borders instead of at the centre of the crater, while the cooled products gather in the centre instead of at the borders. But on the earth the solid crust forcibly represses the steam gathering beneath until it has accumulated strength for an explosion, while there is no such restraining power that we know of in the sun. Zöllner, indeed adapted his theory of the solar constitution to the special purpose of procuring it, yet with very partial success, since almost every new fact has proved adverse to his assumptions. Volcanic action is essentially spasmodic. It implies habitual constraint, varied by temporary outbreaks, inconceivable in a gaseous globe such as we believe the sun to be. If the volcanic hypothesis represented the truth, no spot could possibly appear without a precedent eruption. The real order of the phenomenon, however, is exceedingly difficult to ascertain, nor is it perhaps invariable. Although in most cases the opening shows first, that may be simply because it is more easily seen. According to Father Sidgreaves, the disturbance has then already passed the incipient stage. He considers it indeed highly probable that the preparatory sign of a new spot is always a small, bright patch of facula. This sequence, if established, would be fatal to Lockyer's theory of sun spots, communicated to the Royal Society May 6, 1886, and further developed some months later in his work on the chemistry of the sun. Spots are represented in it as incidental to a vast system of solar atmospheric circulation, starting with the polar out and up flows indicated by observations during some total eclipses, and eventuating in the plunge downward from great heights upon the photosphere of prodigious masses of condensed materials. From these falls result primarily spots, secondarily through the answering uprushes, in which chemical and mechanical forces cooperate, their girdles of flame prominences. The evidence is, however, slight that such a circulatory flow as would be needed to maintain this supposed cycle of occurrences really prevails in the sun's atmosphere, and a similar objection applies to an anticyclonic theory, so to designate it, elaborated by Egon von Apolzer in 1893. August Schmidt's optical rationale of solar phenomena was, on the other hand, a complete novelty both in principle and development. Attractive to speculators from its recondite nature and far-reaching scope, it by no means commended itself to practical observers, intolerant of finding the all but palpable realities of their daily experience dealt with as illusory products of circular refraction. A singular circumstance has now to be recounted. On the 1st of September, 1859, while Carrington was engaged in his daily work of measuring the positions of sun-spots, he was startled by the sudden appearance of two patches of peculiarly intense light within the area of the largest group visible. His first idea was that a ray of unmitigated sunshine had penetrated the screen employed to reduce the brilliancy of the image. But having quickly convinced himself to the contrary, he ran to summon an additional witness of an unmistakably remarkable occurrence. On his return, he was disappointed to find the strange luminous outburst already on the wane. Shortly afterwards the last trace vanished. Its entire duration was 5 minutes, from 11.18 to 11.23 a.m. Greenwich time, and during those 5 minutes it had traversed a space estimated at 35,000 miles. No perceptible change took place in the details of the group of spots visited by this transitory conflagration, which, it was accordingly inferred, took place at a considerable height above it. Carrington's account was precisely confirmed by an observation made at Highgate. Mr. R. Hodgson described the appearance seen by him as that of a very brilliant star of light, much brighter than the sun's surface, most dazzling to the protected eye, illuminating the upper edges of the adjacent spots and streaks, not unlike, in effect, the edging of the clouds at sunset. This unique phenomenon seemed as if specially designed to accentuate the inference of a sympathetic relation between the earth and the sun. From the 28th of August to the 4th of September, 1859, a magnetic storm of unparalleled intensity, extent, and duration was in progress over the entire globe. Telegraphic communication was everywhere interrupted, except indeed that it was in some cases found practicable to work the lines without batteries, by the agency of the earth currents alone. Sparks issued from the wires, gorgeous aurorae draped the skies in solemn crimson over both hemispheres and even within the tropics. The magnetic needle lost all trace of continuity in its movements, and darted to and fro as if stricken with inexplicable panic. The coincidence was drawn even closer. At the very instant of the solar outburst, witnessed by Carrington and Hodgson, the photographic apparatus at Kew registered a marked disturbance of all the three magnetic elements, while shortly after the ensuing midnight the electric agitation culminated, thrilling the earth with subtle vibrations and lighting up the atmosphere from pole to pole with the coruscating splendours which perhaps dimly recall the times when our ancient planet itself shone as a star. Here, then, at least, the sun was, in Professor Balfour Stewart's phrase, taken in the act of stirring up terrestrial commotions, nor have instances since been wanting of an indubitable connection between outbreaks of individual spots and magnetic disturbances. 4 such were registered in 1882, and symptoms of the same kind, including the beautiful rose aurora, marked the progress across the sun of the enormous spot group of February 1892, the largest ever recorded at Greenwich. This extraordinary formation, which covered about 1/300th of the sun's disk, survived through 5 complete rotations. It was remarkable for a persistent drift in latitude, its place altering progressively from 17 degrees to 30 degrees south of the solar equator. Again, the central passage of an enormous spot on September 9, 1898, synchronized with a sharp magnetic disturbance and brilliant aurora, and the coincidence was substantially repeated in March 1899, when it was emphasized by the prevalent cosmic calm. The theory of the connection is indeed far from clear. Lord Kelvin in 1892 pronounced against the possibility of any direct magnetic action by the sun upon the earth, on the ground of its involving an extravagant output of energy. But the fact is unquestionable that, in Professor Bigelow's words, abnormal agitations affect the sun and the earth as a whole and at the same time. The nearer approach to the event of September 1, 1859, was photographically observed by Professor George E. Hale at Chicago, July 15, 1892. An active spot in the southern hemisphere was the scene of this curiously sudden manifestation. During an interval of 12 minutes between 2 successive exposures, a bridge of dazzling light was found to have spanned the boundary line dividing the twin nuclei of the spot, and these, after another 27 minutes, were themselves almost obliterated by an overflow of far-spreading brilliancy. Yet 2 hours later, no trace of the outburst remained, the spot and its attendant faculae remaining just as they had been previously to its occurrence. Unlike that seen by Carrington, it was accompanied by no exceptional magnetic phenomena, although a storm set in next day. Possibly a terrestrial analogue to the former might be discovered in the auroral beam, which traversed the heavens during a vivid display of polar lights, November 17, 1882, and shared, there is every reason to believe, their electrical origin and character. Meantime, M. Rudolf Wolf, transferred to the direction of the Zurich Observatory, where he died December 6, 1893, had relaxed none of his zeal in the investigation of sun-spot periodicity. A laborious revision of the entire subject, with the aid of fresh materials, led him in 1859 to the conclusion that while the mean period differed little from that arrived at in 1852 of 11.11 years, very considerable fluctuations on either side of that mean were rather the rule than the exception. Indeed, the phrase "sun-spot period" must be understood as fitting very loosely the great fact it is taken to represent, so loosely that the interval between two maxima may rise to 16½ or sink below 7½ years. In 1861, Wolf showed, and the remark was fully confirmed at Kew, that the shortest periods brought the most acute crises, and vice versa, as if for each wave of disturbance a strictly equal amount of energy were available, which might spend itself lavishly and rapidly, or slowly and parsimoniously, but could in no case be exceeded. The further inclusion of recurring solar commotions within a cycle of 55½ years was simultaneously pointed out, and Hermann Fritz showed soon afterwards that the aurora borealis is subject to an identical double periodicity. The same inquirer has more recently detected both for aurorae and sun-spots a secular period of 222 years, and the Kew observations indicate for the latter oscillations accomplished within 26 and 24 days, depending most likely upon the rotation of the sun. This is certainly reflected in magnetic and perhaps in auroral periodicity. The more closely, in fact, spot fluctuations are looked into, the more complex they prove. Maxima of one order are superposed upon, or in part neutralized by, maxima of another order. Originating causes are masked by modifying causes. The larger waves of the commotion are indented with minor undulations, and these again crisped with tiny ripples, while the whole rises and falls with the swell of the great secular wave, scarcely perceptible in its progress because so vast in scale. The idea that solar maculation depends in some way upon the position of the planets occurred to Galileo in 1612. It has been industriously sifted by a whole bevy of modern solar physicists. Wolf, in 1859, found reason to believe that the 11-year curve is determined by the action of Jupiter, modified by that of Saturn, and diversified by influences proceeding from the Earth and Venus. Its tempting approach to agreement with Jupiter's period of revolution round the sun indeed irresistibly suggested a causal connection, yet it does not seem that the most skilful coaxing of figures can bring about a fundamental harmony. Carrington pointed out in 1863 that while during 8 successive periods from 1770 downwards there were approximate coincidences between Jupiter's aphelion passages and sun-spot maxima, the relation had been almost exactly reversed in the 2 periods preceding that date, and Wolf himself finally concluded that the Jovian origin must be abandoned. M. Duponchel's prediction, nevertheless, of an abnormal retardation of the maximum, due in 1881 through certain peculiarities in the positions of Uranus and Neptune about the time it fell due, was partially verified by the event, since after an abortive phase of agitation in April 1882, the final outburst was postponed to January 1894. The interval was thus 13.5 instead of 11.1 years, and it is noticeable that the delay affected chiefly the southern hemisphere. Alternations of activity in the solar hemispheres were indeed a marked feature of the maximum of 1884, which in Mr. Fay's view derived thence its indecisive character, while sharp, strong crises arise with the simultaneous advance of agitation north and south of the solar equator. The curve of magnetic disturbance followed with its usual strict fidelity the anomalous fluctuations of the sun-spot curve. The ensuing minimum occurred early in 1889 and was succeeded in 1894 by a maximum slightly less feeble than its predecessor. It cannot be said that much progress has been made towards the disclosure of the cause or causes of the sun-spot cycle. No external influence adequate to the effect has at any rate yet been pointed out. Most thinkers on this difficult subject provide a quasi-explanation of the periodicity in question through certain assumed vicissitudes affecting internal processes. Sir Norman Lockyer and E. von Oppolzer reached the same end by establishing self-compensatory fluctuations in the solar atmospheric circulation. Dr. Schuster resorts to changes in the electrical conductivity of space near the sun. In all these theories, however, the course of transition is arbitrarily arranged to suit a period, which imposes itself as a fact, peremptorily claiming admittance, while obstinately defying explanation. The question so much discussed as to the influence of sunspots on weather does not admit of a satisfactory answer. The facts of meteorology are too complex for easy or certain classification. Effects owning dependence on one cause often wear the livery of another. The meaning of observed particulars may be inverted by situation, and yet it is only by the collection and collocation of particulars that we can hope to reach any general law. There is, however, a good deal of evidence to support the opinion, the grounds for which were primarily derived from the labours of Dr. Meldrum at Mauritius, that increased rainfall and atmospheric agitation attend spot maxima, while Herschel's conjecture of a more copious emission of light and heat about the same epochs has recently obtained some countenance from Sabalyev's measures showing a gain in the strength of the sun's radiation pari passu with increase in the number of spots visible on its surface. The examination of what we may call the texture of the sun's surface derived new interest from a remarkable announcement made by Mr. James Nasmyth in 1862. He had made, as he supposed, the discovery that the entire luminous stratum of the sun is composed of a multitude of elongated shining objects on a darker background, shaped much like willow leaves, of vast size, crossing each other in all possible directions, and possessed of unceasing relative motions. A lively controversy ensued. In England and abroad the most powerful telescopes were directed to a scrutiny encompassed with varied difficulties. Mr. Dawes was especially emphatic in declaring that Nasmyth's willow leaves were nothing more than the nodules of Sir William Herschel seen under a misleading aspect of uniformity, and there is little doubt that he was right. It is nevertheless admitted that something of the kind may be seen in the penumbrae and bridges of spots, presenting an appearance compared by Dawes himself in 1852 to that of a piece of coarse straw thatching left untrimmed at the edges. The term granulated, suggested by Dawes in 1864, best describes the mottled aspect of the solar disk as shown by modern telescopes and cameras. The grains, or rather the floccules, with which it is thickly strewn, have been resolved by Langley, under exceptionally favourable conditions, into granules not above 100 miles in diameter, and from these relatively minute elements, composing jointly about one-fifth of the visible photosphere, he estimates that three-quarters of the entire light of the sun are derived. Janssen agrees so far as to say that if the whole surface were as bright as its brightest parts, its luminous emission would be 10 to 20 times greater than it actually is. The rapid changes in the forms of these solar cloud summits are beautifully shown in the marvellous photographs taken by Janssen at Meudon, with exposures reduced at times to 1/100,000th of a second. By their means also the curious phenomenon known as the réseau photosphérique has been made evident. This consists in the diffusion over the entire disk of fleeting blurred patches separated by a reticulation of sharply outlined and regularly arranged granules. The imperfect definition in the smudged areas may be due to agitations in the solar or terrestrial atmosphere, unless it be, as Dr. Schemmer thinks possible, merely a photographic effect. M. Janssen considers that the photospheric cloudlets change their shape and character with the progress of the sunspot period, but this is as yet uncertain. The grains, or more brilliant parts of the photosphere, are now generally held to represent the upper termination of ascending and condensing currents, while the darker interstices, Herschel's pores, mark the positions of descending cooler ones. In the penumbræ of spots, the glowing streams rushing up from the tremendous sub-solar furnace are bent sideways by the powerful indraft, so as to change their vertical for a nearly horizontal motion, and are thus taken as it were in flank by the eye, instead of being seen end-on in mamelon form. This gives a plausible explanation of the channeled structure of penumbræ, which suggested the comparison to a rude thatch. Accepting this theory as in the main correct, we perceive that the very same circulatory process, which in its spasms of activity gives rise to spots, produces in its regular course the singular marbled appearance, for the recording of which we are no longer at the mercy of the fugitive or delusive impressions of the human retina. And precisely this circulatory process it is which gives to our great luminary its permanence as a sun or warming and illuminating body. End of Chapter 2, Part 2.